Okay, any questions about this vector addition, multiplication, the components of vectors, etc.? Okay, let's do some applications then. How many of you remember this cosine theorem? I mean, the question that comes to my mind, why do you remember such a theorem at all? Okay, let's derive it. I mean, you will see that the derivation using vector, I mean, if you want to derive them without using vectors, it takes pages. But we will see that once you get used to using vectors, it's just a couple of lines. So you don't have to memorize all these cosine theorem. You can just derive it. Now, this theorem is basically about the sides of triangles. So let's say you have a triangle. This is A, this is B, this is C. Let's say this is the angle theta. Then cosine theorem tells you that C squared is equal to A squared plus B squared plus or minus 2AB cosine theta. It should be minus. Minus 2AB cosine theta. So let's derive it using vectors. Now what we are interested in is the side of this length. So let's just write it as a vector. So let's say this is our vector C. This is our C vector. We have the side with the length A. Let us define a vector that has the same length and that goes along this side as the vector A. This is the vector A, and this is the vector, let's call it the vector B. So we have this triangle, and we have defined three vectors. Each one has the magnitude, the length of a given side, and it's along that side. Once we have this, the vector C is nothing but the vector A plus the vector B. Now C squared is nothing but the magnitude of this vector squared. But if we have a vector, if you take the square of that vector, that gives you the magnitude of that vector squared. The vector C squared is nothing but its magnitude squared. But the vector C I can also write in terms of A and B. This is equal to A plus B all squared. I can just open up that parenthesis. That is A squared plus B squared plus 2A dot B. So C squared is equal to, okay, A squared is the magnitude of this side squared. Well, the magnitude of that side is nothing but A. Plus, now B squared is the magnitude of this vector squared, but the magnitude of that vector is the length of that side. Okay, so what is A dot B? Which is small a times b, the magnitude, and then cosine of cosine theta, cosine pi minus theta, sine theta. Okay, so the alternatives: cosine theta, sine theta, cosine pi minus theta. Well, let me also add sine pi minus theta. Okay, remember the definition of the scalar product. The cosine of the angle between the two vectors. If you just bring the vectors, the ends of the vectors together, if this is one vector, this is the other vector, then this angle you have to multiply it by the cosine of that angle. Now if you look at this A vector and the B vector, their endpoints are not at the same point. So first you have to make sure that their endpoints are at the same point. So you have to take this, let's say, A vector, move it, the end of that A vector to this point. So basically you will be extending this line. So this, if you bring the A vector to this point, it will just be pointing like this. The angle between the two will be this one, which is pi minus theta. So here we have cosine of pi minus theta a squared plus b squared minus 2ab cosine theta. Okay, any questions on this one? So do you have any questions about vectors in general? Some questions on vectors?
Always we are showing these vectors on linear. Just imagine you have a circle and you have a speed or with a speed, also with a speed vector. And how can you show on the graphs of the continuous? I don't know. Is it possible always directions like this, linear, but maybe another, you got it.
Okay, so that confusion quite often arises. So for example, you take an object, attach it to the end of a string and start to rotate it. What is its velocity? It's not linear, is it like this? It's like a curve? It's changing everything. It's always linear. I mean, we will define now we will start now the motion in 2D and 3D. Two-dimensional and three-dimensional motion. And we will make the definitions. First we will define the things. But we will be using vectors, so it's important that you understand the vectors. At least have some feeling about the vectors. You should understand what we mean by subtracting vectors, what we mean by adding vectors, dividing vectors by numbers, how to use the components. Okay. Now, the motion in 2D and 3D will be almost exactly the same thing as the motion in one dimension. The only difference we will have is in one dimension, we were using just numbers. We were subtracting numbers, adding numbers, multiplying numbers. In the three-dimensional case or two-dimensional case, we will just replace the position, numbers that refer to the position, with their corresponding vector parts. That's the only change we will do. The definitions will be identical. So let's first discuss with the position vector. Again, you should take a reference point. This is your reference point, let's denote it by O. If this is your object, sitting over there, then the position vector of that object, we will usually use the symbol R to denote the position. This is the R. Then the position might be changing in time. Then we will be talking about the displacement. That is delta R. Well, I think your book uses this notation, the small delta. Do you remember how we defined the displacement in the one-dimensional case? Okay, somebody else. I always see the same hands. Okay, in the one-dimensional case, it was just x final, which was the final position, minus x initial, which was the initial position. We do the same thing over here. The displacement is its final position minus the initial position. This is a position vector, Ri. We should know how to multiply it by a minus 1. It will be a vector of the same magnitude, just pointing in the opposite direction. And we just add that minus Ri to the final position. So this will be the displacement vector. So for example, if we have this, let's say this is our reference point. This is the initial point of my object. This is the final point of position of my object. Then the displacement vector is just the vector that points from the initial position to the final position. The object has moved from this point to that point in that direction with this length. So this is delta R. Now we can also write this in terms of the components. If you just write the initial point as the x component is, let's say, xi in the x direction plus yi in the y direction plus zi in the z direction. And similarly for the final point, x final in the x direction, y final in the y direction plus z final in the z direction. Then the displacement vector will be just the difference of these two. X final minus x initial in the x direction plus y final minus y initial in the y direction plus z final minus z initial in the z direction. If you look at the components one by one, x final minus x initial, y final minus y initial, z final minus z initial, it's just identical expression that we use in the one-dimensional case. So at least for the time being, the displacement vector, at least the components of the displacement vector just behave as if it is a one-dimensional problem. So the three-dimensional problem, in a sense, we will see that it's more general for the velocity, for the acceleration, etc. The three-dimensional problem just reduces to, in kinematics at least, to three independent one-dimensional problems. Now there is one major distinction though. If you look at the one-dimensional case, if an object is being displaced, its distance from the origin will always change. So you cannot, if this is your reference point, your object is at this point initially and at this point finally, its distance changes. So that is a net displacement. But in two-dimensional or three-dimensional, we have this rotational motion also possible. So you have this is the initial position. The final position can be over here. It is at the same distance from the origin, but it has moved. So the position vector, although its magnitude doesn't change, its direction does change. So that gives us a displacement. So since the vector has these two properties, its magnitude and its direction, if any one of these changes, it gives us a different vector. And hence there is a net change in that vector. In this case, it is the position. The position changes, so we have this displacement vector. It will be more important when we discuss, for example, velocities. Your friend was asking about what happens if it's moving, if it has a circular motion. Its velocity, although the magnitude is always the same, the velocity is always changing. And hence it has an acceleration. Let's define those also. We will be defining them in a moment. So this is the displacement. Now if we have the displacement, we can talk about what about the displacement per unit time. That is what we call the velocity. The average velocity we will define as the displacement vector divided by the time it takes. This is how we define it. And well, this is a vector, delta r, the displacement, is the difference of two vectors, and hence it's itself a vector. We are multiplying a vector by a number, that is the inverse time, but we had already seen that if you have a vector, if you multiply it by a number, it is again a vector. So the velocity is a vector. It both has a direction and a magnitude. Now in terms of the components, we already have this one. We know that multiplying a vector by a number, if we want to write them in terms of the components, we just multiply each one of the components separately. So this is x final minus x initial divided by delta t, y final minus y initial divided by delta t, plus z final minus z initial divided by delta t, which we can also write as the average velocity, the x component, average velocity in the y component, average velocity, it's z component. So again, if you just compare the x, y, and z, if you just look at the x, y, and z components, we use exactly the same definition that we use in one-dimensional case. We are basically repeating the same thing. The x component will be delta x over delta t, y component delta y over delta t, and the z component is delta z by delta t. And this is the average velocity. We can also define the instantaneous velocity limit as delta t goes to 0 of delta r by delta t, which we just call the derivative of r by t. This is the instantaneous velocity. Again, the definitions are, if you just look at formally, if you remove these vector arrows, it just becomes a one-dimensional equation. The equations are identical. They even mean almost identical. And finally, we can define the acceleration. Well, I'm kind of going fast over these because they're just exactly the same thing that we did in one dimension. So if you have any questions, please ask. The average acceleration will be delta v by delta t. And again, in terms of the components, this will be delta, the change in the x component, divided by delta t in the x direction, the change in the y component, divided by delta t, the change in the z component, divided by delta t. And similarly for the instantaneous velocity, instantaneous acceleration, you just take the limit as delta t goes to 0. Now, let's go back to the example that your friend has asked. We have this object that is doing circular motion. Okay, so we have this object fixed over here. It's doing some circular motion. We start from here. We wait for some time and it comes here. Let me sketch it. It is dv. This is the orbit of my object. My object starts here, let's say, at time t equal to 0. The radius, let's say, is how long should the radius be? 3 meters, okay. 3 meters. At time t equal to 2 seconds, it's somewhere over here. And let's assume that you are given the information that the speed is constant. The speed is 2 meters per second, constant. What is the average acceleration of this object? Zero.
There's no acceleration. It's constant.
Okay. The average acceleration is 0. Okay, you can try to solve it. I want some answers. Or if you agree with the 0, you can also say that you also think it is 0.
Its magnitude is 4 meters per second, and people is points center of the circle.
Okay, towards the center. 4/3, okay. It's in the same direction, but 1 meters per second squared. Anybody trying to solve? Do you stick with your answer or do you want to change your answer?
Yeah, I want to change, but
You are just withdrawing your answer. Okay. Okay, so he gave up on his answer. Okay, so we again have that 0 answer. Sure.
I think when the 1 second, the speed, the velocity is minimum, and the speed is maximum.
Okay, so the velocity changes.
Yes, velocity changes because the acceleration, displacement, light.
So if the velocity changes, why do you think that the acceleration is 0? Acceleration is proportional to the velocity change.
At the end of the second two, the velocity reach the start velocity and velocity is equal.
Oh, okay. So that's why. So you are saying that the velocity is constantly changing, but the beginning, the initial and the final velocities are the same, so the acceleration is 0. Okay.
I try to find the velocity vector and to sum each other. And found 8 minus 8 cos alpha, and I found that
Alpha is 8 over 9.
It's an angle I don't know.
So this is your answer?
No, cos.
Cosine of that angle.
8 over 9
Okay.
meter angle.
Okay, I just realized.
Unit meter in the 8 over 9.
Okay, so 8 over 9 meters.
And angle or not.
Okay, so this is 8 over 9 meters, you mean?
Yes.
Okay. I will not make any comments on your answers until you are done. Well, I am about to begin to explain or solve.
You need the angle to calculate.
Okay, I have just realized that I am missing the angle. So let's just assume that this is pi over 3. Okay, so let's try to solve it with this information, with the pi over 3 also added. Okay, we want to calculate the acceleration, so we first have to determine what is the initial velocity, what is the final velocity. We are given the information necessary to calculate both of them. So initially it's moving, okay, it's moving on this line, so initially it's moving, let's say, upwards at t equal to 0. Its magnitude is 2 meters per second. So this is our initial velocity vector, v initial. The magnitude of v initial is equal to s. At 2 seconds, it has rotated by pi over 3 radians or 60 degrees. So it is now over here. This is v final. The magnitude of v final is also equal to s. This is pi over 3. Now the v final minus v initial, delta v, is equal to v final minus v initial. Well, what we do is to calculate this one, just rotate v initial rather than from here to there. Minus v initial, you can just think of it as a vector from here to here. You add v final. So this delta v vector is nothing but this vector over here. This is the direction of delta v. And this side is equal to this side. The angle over here is 60 degrees, so this is an equilateral triangle. Delta v, the magnitude of delta v, is also 2 meters per second. Now the acceleration we have, it has two properties. We have to determine its direction and also its magnitude. The average acceleration was defined as delta v over delta t. So the magnitude of the average acceleration is equal to magnitude of delta v, which we just have said that it is 2 meters per second. Delta t is 2 seconds, so it is 1 meters per second squared. Its direction is in this direction. It's in the same direction. Well, it is pointing towards the center. Well, if you are sitting over here, it's definitely not pointing towards the center. If you are sitting over here, again, it's definitely not pointing towards the center. If you are sitting over here, it is of course pointing towards the center, but I mean, just pointing towards the center, from which point? It's not a direction. It's not enough to say the direction of this vector.
How is it equal to find 1 meter per second squared in without the gave us 60? The angle is
Okay, you shouldn't ask that to me. I'm quite surprised that anybody can get any answer without this information. You see, if this angle was close to 0, this angle over here would be very small, delta v would be very small, and if delta v is very small, then the acceleration will be, the average acceleration, well, it won't be necessarily small, but delta v would be small, its direction will be different, etc.
You can find the angle by using the speed and
What is this? Oh, yeah. Okay. That's also true. No, hold on. We know the speed. We know. No, how do we find it? In 2 seconds, how far away it moves. Yeah, you can find the angle. True, true. I mean, this won't be pi over 3 then. That, Well, let's look at the angle. Well, let me erase this. This is not pi over 3. This is now, let's say, theta. This is theta. Now, what is theta? What is the distance it has covered? S times delta t, which is 2 meters per second, times 2 seconds, which is 4 meters. Divided by the radius, 2 meters. No, 3 meters. Divided by 3 meters, divided by 3 meters, it is 4 over 3. So that is the angle theta. Okay, so these are all wrong. Okay, 4 over 3, is it smaller than 90 degrees or larger than 90 degrees? 4 over 3 radians. Okay, 90 degrees corresponds to pi over 2. Pi is something like 3.1, so this is 1.6. 4 over 3, this is something like 1.3. It is smaller than 90 degrees. So this sketch is still correct. I mean, smaller than 90 degrees. Now, what is delta V? Delta V would be, let's just imagine this line that just divides this angle into 2. This is 2/3, this is 2/3. And this side, since this is an isosceles triangle now, this side is equal to this side. So this side is equal to that side. And one of those sides will be twice. The speed is 2 meters per second times sine 2/3. So this is 4 sine 2/3 meters per second. This is the magnitude of delta V. And the magnitude of the average acceleration will be, just divide by delta t, it is 2 sine 2/3 meters per second squared. Okay. Again, the direction is still this one. There is no analytical closed form for that angle, but if you want, you can just calculate that angle. Yeah, this 4/3 angle, and you are basically done. Okay, the acceleration doesn't change, the speed doesn't change, but nevertheless you have the acceleration. That is one thing. Since they are all pointing in the initial and the final velocity, they are pointing in different directions. We don't come back to our initial velocity. There's a non-zero acceleration. Its direction is not towards the center. Right? If you want to say towards the center, then you should also tell me from which point is it pointing towards the center. And here we are not talking about the acceleration of this object at a particular point, but rather the average acceleration as it's moving along this line. Now the velocity is always straight. It's the linear velocity. It's not a curved object. So the velocity is not going like this. It's just the velocity is always straight. It starts first vertically upward, then it rotates in the counterclockwise sense, and hence it has an acceleration. The acceleration just tells us that it is changing. Acceleration is again linear, and it is pointing, well, somewhere like this. The average acceleration during this motion is pointing somewhere in that direction. Any questions on this one? And we will be studying this circular motion in more detail, but at least for the time within this part.
Why did we use 2, 3?
Well, you see, we had found that the angle was 4/3 radians. So here I have an isosceles triangle. I just divided it into two, forming these two right triangles. So it's just made my life easier. You can as well use the cosine theorem that we had just derived. But in this case, since the speed is constant, just dividing it into two right triangles, two identical right triangles, gave me an easier way to calculate this, the length of the vector delta v.
Delta velocity, the final velocity minus initial velocity.
Yes, delta v is final minus initial.
Why don't we take initial velocity
Why don't we?
the initial velocity minus
Now, why don't we define it the other way around in this one? Now, this vector is v final minus v initial. Remember how we calculate this one. We have the v initial, we take the minus of it, we just need to change its orientation. So if this is our v initial, minus v initial is this one. This is minus vi. We have this minus vi vector, we add the v final vector, and we reach this point. So this v final plus minus vi is the vector that starts from the end of minus vi, which is over here, goes to the head of the v final. So it's this vector. Other questions? Now let's just take a smaller angle. We have this circular motion. We start here. The magnitude of the velocity, let's just call it v0. Let's just say it is constant. Just a constant v0. We start from here. What is the direction of the initial? Let's just assume that it's just moving upward. This is v initial. The magnitude is again v0. And at a later time, at a very small amount of later time, what we are trying to do now is calculate the instantaneous acceleration, let's say at this instant. And we had defined it as the limit of delta v by delta t as delta t goes to 0. So what I have to do is, I know the velocity vector at this point. I can take a very small delta t. In a very small delta t, it will just go over a very small angle. It will go over here. And this will be the new velocity, v final. This is a very small angle. This is the change in the angle theta, let's say, delta theta. Or if we just draw the vectors again, this is vi. I'm just enlarging them a bit. This is vf. They both have the same radius, same length, same magnitude v0. And this angle over here would be just delta theta. Well, I can just imagine a circle with the center over here with radius v0. That's just an imaginary circle. I know that both of the endpoints of these two vectors will lie on the circle because they both have the same magnitude. Now we know what the delta V is. Delta V vector is a vector connecting this endpoint head to this head. So this is my delta V. This is delta V. The magnitude of delta V you see, I have this orange vector delta V. I also have this very small blue arc over there. They almost overlap. Okay, one is straight, one is a bit curved, but they are both of them are so small that they overlap. So their lengths are almost the same. Not exactly, but almost the same. Do you agree? Well, if their lengths are almost the same, then the length of delta V, I can just assume it is the length of that arc. But the length of that an arc is nothing but the radius of the circle, which is, well, in this case it is V0 times the angle, delta theta. So this is the magnitude of delta V. Well, we can just put it over here. So the magnitude of acceleration is V0 times the limit as delta t goes to 0, delta theta by delta t. Now we can do one more thing though. Look at this circle now, the actual circle. Delta theta is just this angle over here. Well, we know that that angle is nothing but the length of this arc divided by the radius of this circle. Let's just call it capital R. So delta theta is nothing but the length of that arc. Well, the length of that arc is nothing but the speed times time, delta t, divided by r. This is r delta theta. So you see, delta theta over delta t is nothing but the speed over the radius. And it's constant, it doesn't change in time. It doesn't depend on this delta t anymore. So since it's just constant, we can just take this limit. So the magnitude of the acceleration is V0 times, well, this ratio is V0 squared over V0 over R. Okay. That ratio, delta theta over delta t, is nothing but V0 over R. We have one V0 over here, so it's already V0 squared over R. So we know the magnitude of the acceleration. If speed is constant, if we are moving on a circle with constant speed, then still, although the speed is constant, the velocity is changing its direction, there is an acceleration. This is the magnitude of the acceleration. What is the direction of the acceleration? Now we will come to the point that this is the magnitude of the instantaneous acceleration right at this point. And you see, this is the initial velocity vector. Acceleration is in the direction of this delta v. And delta v is almost perpendicular to vi. Now, what is that angle? What is this angle?
Pi minus delta theta over 2.
Or pi over 2 minus delta theta over 2. Because here again we have an isosceles triangles, the two sides are equal, so these two angles are equal. So each one of them is pi over 2 minus delta theta over 2. Well, we are taking the limit as delta theta goes to 0, delta t goes to 0, sorry. But if delta t goes to 0, delta theta also goes to 0. So that angle, that is the angle between the acceleration, the direction of the acceleration, and the velocity vector goes to pi over 2. That's 90 degrees. So this acceleration is perpendicular to the velocity vector, well, it's pointing in that direction. Well, that is towards the center, and this is the magnitude of the acceleration. So that's why most of you had said, okay, this is, in this example, it is towards the center. It is towards the center only if you are talking about the instantaneous acceleration, not the average one. Okay, any last questions? Now these things we will just review also on Tuesday. We will go over them again. You have your pre-report on these things for this weekend. Now in principle, since the add drop ends on Friday, those of you who have added this course only during the add drop period, you should be able to access the pre-report upload page by Saturday. If not, if you cannot access them, just send your pre-reports to me by email.